Everything in our scientific intuition says the world is what it looks like. And the whole point of quantum mechanics is that we look in the world and what we see is something a little bit different than what the world really is. Quantum mechanics is central to modern technology, about the relationships between humans and computers, artificial intelligence, consciousness, minds. It is the way the world works. We're trying to do this just because we want to understand the fundamental nature of reality.
Are you optimistic that we will find a positive and amicable relationship with our technology, or are there dangers?
There's absolutely dangers. There always are. If you imagine that there's a percentage probability that a new technology will literally wipe out all of humanity, what percentage is acceptable? We're changing things rapidly, and you can point to specific things like climate change or nuclear weapons or bioweapons or whatever, but just the fact that we do have these amazing capacities and are rushing pell-mell to put them to use without thinking them through, that's bad. There's no reason to think we can't figure things out, and putting the effort in and recognizing, standing up, facing up to the puzzles that reality presents us with is part of what makes us human and part of what really makes life fun.
The world is changing. Inspiration is everywhere. It has never been so easy to connect, share, and bring people together. We're learning from others and finding the best in ourselves. Challenging our beliefs, sharing our vulnerability, overcoming our fears, transforming ourselves so we can transform the world. How far can we go?
This is London Real. I am Brian Rose. My guest today is...
How did the universe begin? Are we living in a simulation, and will AI take over the world? Well, these are some of the questions that I sat down and talked with Sean Carroll about. He's a physicist at Caltech, where my dad actually went to school, but he spent time training at Harvard and even at MIT, where I studied. And he's here to tell you that quantum mechanics is actually really relevant to you and your life. And I'm always impressed that so many people around the world really want to understand a lot about physics, about cosmology. And Sean is one of the best in the business. He's appeared on the Colbert Report, the History Channel, on the Rogan Experience 3 times. And he really has a great way of showing how this stuff applies to your life. And it's interesting to me how a physics professor from Caltech is more about philosophy, because this stuff affects the way that you and I live today. Quantum mechanics is all around us, and you are gonna love this episode. It taught me a lot about my own life, about the future, and how we all relate to each other. So sit back and enjoy this incredible episode with Sean Carroll. This is London Real. I am Brian Rose. My guest today is Sean Carroll, the American theoretical physicist specializing in quantum mechanics, gravity, and cosmology. Your research explores dark matter, extra dimensions, and the origins of the universe, and your work has been published in the New York Times and New Scientist magazine. You've also made television appearances on History Channel's The Universe, Morgan Freeman's Through the Wormhole, and the Colbert Report. Your latest book, Something Deeply Hidden, has been described by the physicist Brian Cox as an exploration of what it means to exist on this speck of dust in a possibly infinite universe. Sean, welcome to London Real.
Thanks very much for having me.
Great having you here. First of all, what's it like being in London? What does this city mean to you? How is it different than LA, where you're at now? You went to school in Boston. Like, what's the vibe when you land here?
I really enjoy London, for a lot of reasons. Like the cheesiest reason is just that it's a foreign country where they speak English. And as an American, of course, English is the only thing that I speak. So it's a wonderful way to get a different set of experiences. But I just love the charm, the culture, the history. Every little street corner has something going on.
And you're already exploring that. I know you bought like an umbrella. You're heading up to Edinburgh. I mean, you really get into the culture, don't you?
Going to be going to Cambridge, giving the Darwin lectures named after Charles Darwin. So just like everywhere you go, there's resonances of things that happened historically.
And science history here as well. Do you feel that when you're here? Like, wow, some big things happened here.
Tonight I'm giving a talk at the Royal Institution, so where Faraday gave his lectures on electromagnetism and so forth. I was just giving this talk on quantum mechanics last night, and I realized every other name that I mentioned had been doing work a few miles away, one place or the other, from Rutherford to Dirac and so forth.
Yeah, you walk into Westminster Abbey and you see like, Sir Isaac Newton buried there, and it's like, it's heavy.
Yeah.
Heavy duty stuff.
It's right next to Stephen Hawking, right? Yeah.
Right, yeah, he's just newly there as well. I kind of walked over his, I don't know, is that his grave there? Or maybe I don't know if he's buried there, but he's got a,
right, I think it's a memorial.
A memorial there. So, all right, so it feels good to be here. You feel kind of
Very
at home.
I really enjoy it, yeah.
Okay, gotcha.
I eat very well when I'm in London. Actually.
Yeah, maybe you should break the myths about London food. It's because we've had a bad rap here about food in London.
The bad rap is not just invented out of whole cloth. I think that every city has a different food culture, and London. It's very possible to get bad food in London. I think what people don't know is it's just as possible to get good food if you just put a little bit of effort into it. And I mean, either world-class fine dining is absolutely available here, but I just love all the different ethnic restaurants that do things in very creative ways. We went to a place called Scully's the other night, which is, it refuses to say where it's from, but it's clearly a lot of North African influence, lamb tagine kind of things, roasted carrots with so many spices in them that I couldn't even begin to name them.
Yeah, the cultural cuisine is off the hook.
Yeah.
And Indian food is the Mexican food of Britain,
Right.
So in America has great Mexican food. We have great Indian food.
I made the mistake of ordering chicken quesadillas, and why am I going from Los Angeles to London and ordering chicken quesadillas? That was not the best choice I could have made.
How'd they compare?
They were fine,
Okay.
but I'm like, why did I choose this? Get the chicken tikka masala.
Yeah, no, but you're right. It's easy to find bad food and also easy to find really amazing world-class fine dining and even just a curry. I mean, I've had Indian people that tell me that curries are better here than in India. So, so long live London. Look, I want to talk about all sorts of stuff. I want to talk about quantum physics and quantum mechanics and a lot of stuff in your book, but I want to maybe go down a little bit of a memory lane because believe it or not, Sean, I used to be a scientist back in my day.
Totally believe it.
I won the San Diego County Science Fair. I went to the California State Science Fair. I used to build these little homemade cathode ray tubes, and that was my identity when I was a kid.
Right.
I was like a science geek. I later went to MIT, got a degree in mechanical engineering, and graduated the same year I think you got your PhD from Harvard. I didn't realize you then came down and spent some time at MIT.
Of course.
I have such fond memories of being there and of learning the science and being around such a great institution with all these big minds. Again, walking through the infinite corridor at MIT, which is this long corridor. Everything has geeky names at MIT, since everyone is a geek a little bit. But there's all of these epic historical people that went there as well.
Yeah.
What do you remember from your time in Boston?
My first experience was I was a grad student at Harvard, and I found out that you can cross-register for courses at MIT for free. You can just take courses at MIT if you're a student at Harvard. So everyone knew, there was scuttlebutt in the physics departments, which courses were better at MIT and which were better at Harvard. Everyone from MIT came to Harvard to take quantum field theory, but everyone from Harvard went to MIT to take general relativity, which was a subject I was very interested in.
Okay.
So I registered for the course, and I'm on the phone. It was before the internet was really very popular, so you had to call, and they said, yeah, it's in building 6130 or something like that. And I said, yes, but what's the name of the building? And they had to explain to me that 6 was the name of the building. We don't give our buildings names, it's just numbers. The subjects are all numbers, and I never learned the numbers despite spending many years at MIT. I just could not keep the numbers straight in my head.
You're right. I never thought about it, but yeah, building 6, building 7, building 10, and you don't have a major, your course 2 is mechanical engineering, course 1 is civil engineering.
You get the feeling that if they could reduce everything to numbers, they'd be much happier.
What are you trying to say,
eliminate
Sean?
words.
Yeah. No, you're right. That's the ethos of the place. Yeah. And the courses
Despite
at MIT,
having a world-famous linguistics department with Noam Chomsky, right?
Right. Yeah, no, they do have these weird pockets of surprise there. And so were they better at certain, would you say the MIT courses were better at things that were more lab-oriented and research-oriented stuff, and Harvard was better at the theory maybe? Or does it depend on the professor?
Yeah, at the graduate level, it just depends on the professor, right? Okay. I mean, for undergraduates, there's an experience. I think, undergraduate education is really, I think, where you become who you are in some sense, right?
Yeah.
And going to MIT, you're going to become a different person, or you're going to want to be there as a different person than going to Harvard or Penn State or UCLA or whatever, or Caltech for that matter. But once you're in grad school, they're all kind of the same because the grad students come from all these different undergraduate institutions, and it becomes a little bit more mixed. Right. So it was just who's the good professor, yeah. And MIT at the time had really good, and still today has really good teachers of upper level physics courses. So it was a great opportunity to go there.
And how would you say the cultures are different between Harvard and MIT? Because you know.
They're very different, and saying that they're very different matters because honestly, I've been to a lot of universities in a lot of different contexts, and most universities are not that different. You know, the United States has hundreds and hundreds of universities, and most of them are pretty much the same. Okay. And Harvard and MIT and also Caltech, where I am now, are a few of the ones that are really unique. And at MIT, the feeling I always got was that everyone works harder than everyone else. This is their self-image. They keep telling themselves how hard they work, right? And a lot of them are entrepreneurial, right? People starting businesses and things like that. At Caltech, the students also work hard, but no one's going to start a business. They're going to become a professor of something someday.
Right.
And at Harvard, it was neither one of those. It's just we rule the world. We're the ruling class. You know, we are the sons and daughters of princes and sultans and presidents and senators, and we'll be fine. And there's a few quirky artist types in there. Great lacrosse players or whatever. But it was high-achieving people or high-born people and a whole bunch of things who were pretty convinced that they were the world's elite. Right. And it was a little more relaxed for that reason than MIT ever was.
And that's like a powerful thing to install to a young person, that you are expected and you will become a leader of this world in a corporate sense or a political sense.
Our graduation speaker was Al Gore because his daughter was going there, and he had gone there, and Natalie Portman was going there at the time, and you just got used to that kind of thing. And I was not used to that kind of thing, but again, grad school is a little bit different. You're in this research-oriented, very focused world. I think it can be very good. Like if you go to a place like Harvard or MIT, because they are unique, they're not for everybody, but for the right people, they're amazing. The opportunities are just absolutely incredible.
Yeah, no, I think you made a really good assessment there. When I was at MIT, I lived in a fraternity with 50 guys, and I don't ever recall having a conversation about what family they came from or how much money they had or power. All we tried to worry about was who could get a better grade, if we could even make it through this course without dying, how hard we needed to study. And it was a real, I felt like I was in a pressure cooker there. And I liked that because, you knew what you had to do. And if you did it, then you would be successful.
My impression is you wouldn't have a conversation about that at Harvard either because it was just taken for granted, right? But you would, I think that, the difference is the idea of like, oh, let's start a magazine. That's like the kind of thing that we do, right? And that was never part of my upbringing. I came from a long line of steelworkers and secretaries, and so just the idea that we will affect the world in some important way is quite impressive in the sense that it gives you a little bit of a mission, a purpose, if that's what you want.
Yeah, no, very much so. And just to finish out our appraisal of the
reminiscing
of the U.S. college system, Caltech, which is where my father went to school. He graduated in 64 undergraduate, 65 with a master's degree in EE, and he came from a farm in Arizona. So for him, it was quite a culture shock to be there. I went there with him when I was 18 years old to look at the campus. Now, Caltech is probably closer to MIT than any other school as far as they're both very high-level technical institutions, but they're also very different. How would you describe Caltech to people?
Yeah, it is. I would have thought that they were the same or very similar, just East Coast, West Coast, but they're very different. MIT is much bigger, much more diverse. MIT has world-class departments in economics and linguistics and even English. Caltech has one department of humanities and social sciences, and there is, an economist and a couple philosophers and a couple historians, but guess what? They're doing philosophy of science, history of science. The English courses are in science fiction. It's extremely focused on science, and it's much smaller, and it's very top-heavy. There's very few students. The graduating class is like 400 people every year, right. And the number of professors is huge. And almost every university, there's always this thing where if you're a professor, when September has come along and the students have arrived and the campus comes to life. And the Caltech is just no different from day to day because there's just as many people there doing their work every day of the year.
Yeah, I feel like there were smarter people at Caltech when I walked around. But my dad took me to Caltech. I walked around and I saw like a bunch of really intensely smart dudes. And then I went to Boston and I went to a fraternity and the guys got me drunk the night before. And then I went and saw somebody crooning in the subway and I fell in love with the city and I was like, I'm gonna go here.
Yeah.
So,
I mean, well, Boston is a wonderful environment too, especially, you know, both MIT and Harvard, I think, you have the feeling that you're intellectually the center of the world when you're in Cambridge, Massachusetts as a young scholar, one way or the other. You know, there are people coming in, and, you know, there are people who are already there, and it's just exhilarating.
Yeah, and there's like 40 or 50 colleges in the greater Boston area.
So many students,
it's just full of this, like you said, you feel like you're in the center of like education.
And because Caltech is so small, and it doesn't make a huge effort to become integrated into the community, there's no feeling in Pasadena that you're in a college town in the same way that there would be in Cambridge or Boston.
Yeah, that's true. All right, good. So if anyone was thinking about any of those institutions, there you go.
They're all great, but they are different. Know that they're different and find the one that works for you would be my advice. Yeah.
Totally agree. The last thing you would want is to, want a degree in politics from Harvard and go to MIT. I mean, you would want to run away from that place and vice versa.
Yeah, exactly.
So yeah, definitely tour the college, get to know who's there. Do you ever look in the mirror and say, wow, this is weird? I'm an expert in quantum physics and I'm on the Colbert Report. You know, that I'm being asked to go on these massive television channels and talk about stuff that maybe when you were younger thought was very esoteric and only would be understood by so many. Are you surprised by how many people actually care about this stuff?
I'm kind of not surprised. I think that there's a bit of a reputation, or at least a cliche or something like that, when you mention physics, or especially the more out there areas of quantum physics or cosmology, to sort of act intimidated and afraid of it. But I think that once you get past that, there's a lot of people who genuinely have a real interest in this stuff. And when we scientists make the effort to make it a little bit more accessible, a little bit more understandable, a little bit more human and relatable, there's a huge positive reaction to that. It is funny though, so I'll admit, like I was on the Colbert Report, and that's the one thing I've done in my life that will always get mentioned when I get introduced. So it's like my best accomplishment so far. But in the US, for American listeners here, he was on Comedy Central, cable channel. Now he's moved to CBS, a network channel, and the show has changed, and I don't appear on the show anymore. And part of that is when he was on cable, he could sit down with a person for 5 minutes and have a conversation with anybody, with a writer, a historian, philosopher, scientist. And now that he's on network TV and it's kind of broader, there has to be kind of a spectacle. So there's still scientists appearing, but they're doing demonstrations and blowing things up and so forth, which is not my gig, right? I'm going to sit down and talk about the nature of reality, and they're like, yeah, we're not, we kind of don't do that anymore. So there's still, a lot of people who are in the TV world have that intimidation about science that I think is kind of a shame.
Yeah, well, it's still kind of a shame that TV is about the 5 minute, the spectacle, the pow, the boom. Whereas I know you have a podcast, and what we do here is long form, and people can get as much as they want, and they love it. And you've been on things like the Joe Rogan Experience, where people will listen to you for 3 hours, and it's an amazing thing to have this kind of media on tap that people can have.
And it's not for everybody. Like my podcast is for a general audience. It's called Mindscape, and it's for people who are not scientists or whatever. But it is for people who are sufficiently interested to listen to a 1 or 2 hour conversation with an expert trying to get into the details of what they're doing. So no prerequisites, no knowledge assumed, but the inquisitiveness, the curiosity is definitely assumed. And it's just been great to feel that people really respond to it.
Yeah, I love it. All right, how do we get into this? Because I'm just now picturing my aunt who's in Denver, who's in her 70s, and I'm just thinking, okay, Marianne, how do we convince her that maybe learning about quantum is important? And how do you first start having these conversations?
Yeah, there's a lot of it. It's just like picking a university. Different people will get into it for different reasons, right? I mean, there are people who just care about the fact that quantum mechanics is central to modern technology. Quantum mechanics, just to back up a little bit, it is the way the world works. It's the replacement for classical mechanics that Isaac Newton came up with in the 1600s. And after Newton came up with classical mechanics, that's what you were tortured with as an undergraduate, with pulleys and levers and inclined planes, right?
Yes, the basic physics we kind of all learned in high school which seemed really simple. You've got the gravity, you've got, like you said, the this does the this, and then everything plugs in perfectly.
That's right. And it was clean, crisp, literally the clockwork universe, right? That was Newtonian mechanics. And it was so good and so compelling that people thought, that's how the world works. And it was not really, Newtonian mechanics is not a specific theory, it's a paradigm, it's a way of doing physics. And it applies whether you're talking about particles or electricity and magnetism, the planets or whatever, the ocean currents. And then in the early 20th century, we began to realize, it doesn't quite work that way.
All the time.
It doesn't, it's fundamentally not just you take Newtonian mechanics and tweak it a little bit. Fundamentally, you throw it out and you replace it with something totally different. And that's what quantum mechanics asks us to do. And the central idea that makes quantum mechanics different is that in Newtonian mechanics, you have there's a planet going around the sun. You give me where the planet is, how fast it's moving, where the sun is, and I can tell you what it's going to do. And literally people do this on computers, right? They simulate the future of the solar system.
Right, and Kepler used to do that in the back
Kepler,
in the day.
Galileo, Newton,
all those
people,
guys used to
Robert
watch
Hooke,
it.
yes.
And that was all based on Newtonian.
Well, Kepler was pre-Newton. Kepler helped
pre-Newton.
inspire Newton to figure these things out. Kepler figured out that planets move in ellipses, not in perfect circles.
Right.
And then Newton said, oh yes, if the law of gravity is the inverse square law, I can predict that planets move on ellipses. So that was his great triumph.
Right.
But then the difference is in quantum mechanics, if you talk about an electron, for example, okay? In fact, the electron, there's the classic picture of the atom that we've all seen with a little nucleus at the middle, and the electrons are what look like little planets, almost just like a little solar system, right?
Right.
So that's a very comforting picture. We've seen pictures of the solar system. Here's the atom. They look very similar.
Perfect circle. It's all happy and perfect.
That's right. And as it turns out, that picture of the atom is complete BS. It's not what atoms really look like. And you know that because an electron zooming around an atom would give off light. All of the light that we see here in this room is from electrons jiggling up and down, emitting radiation. And therefore, the electron would spiral into the middle. It would lose energy. It's not a stable configuration. So the answer as to why electrons stay in their atoms is that they're not little particles moving on orbits. They're waves. They're a cloud that is spread out and sort of settles into some minimum energy configuration. So this is, we're talking about now 1910s, people figured this out. If you think about electrons as little clouds, everything's okay.
Right.
The problem is when you look at an electron, when you shoot an electron through a detector, you don't see a big cloud spreading out. You see a particle moving along a line, right? And believe it or not, the thing that physicists convinced themselves of in the 1920s was, here's how to describe reality. When you're not looking at it, the electron is a wave. And then when you look at it, it's a particle. And people like Einstein said, oh, come on. Even if that's true, that can't be the final answer. Let's try to do better. But people like Niels Bohr and his friends said, no, it works. Let's move on. Okay.
And there was like a name for that theory that when you
the Copenhagen interpretation of quantum mechanics.
And when you observe something, it fundamentally changes it. Which people understand that concept, but like you said, it feels like it's a
what do you mean?
together.
So the question is what counts as observing, right? Does it have to be a person?
Yeah.
Could it be a cat? As Schrödinger famously wondered. Could it be a video camera? What if I don't look at it very closely? Does that count?
What if you just look at it?
And the answer is, you're not supposed to ask those questions. The answer is, quantum mechanics seems to, in the way that we teach it to our students at MIT or Caltech, the act of observation is a primitive, fundamental notion. Now, that's kind of silly and absurd and shouldn't be the final answer. So people like me are trying to do better than that. But that's the mystery. That's the reason why quantum mechanics is difficult to understand, because it involves words like measurement and observation that are just not very well defined.
Okay. And I remember being taught that it's a particle and it's a wave and it depends on the time. And growing up in a Newtonian world as a kid and living in this reality, whatever we want to call this, that just doesn't make any sense. Really, now it feels like you're in a religion class, right? A little faith.
Well, it's very interesting because psychologically, the reason why it's hard for physicists to really come to terms with quantum mechanics is everything in our scientific intuition says the world is what it looks like. We look at the world and we see it. And the whole point of quantum mechanics is that we look at the world and what we see is something a little bit different than what the world really is. And so that's very hard to reconcile. And we say, is it that the true reality is something very, very different and we have to give up on the idea that we see the world directly? Or is this set of words about waves and clouds that we use to describe reality just a crutch, and what we see really is the reality? And so that's a debate that's still ongoing.
Okay. Now you're mentioning 1910, 1920 when this stuff starts to get funny. Is that because of Einstein? Is it because also we were able to start to measure things a little bit closer and we started having access to nucleuses and soon to be atomic bombs?
Yeah, very much. Almost all the great revolutions in physics are driven by better data, one way or the other, right? Better experiments. And there were two ideas that really bugged people in the early days of the 20th century. One was what's called black body radiation. So if you just take an object and you heat it up to some temperature, there's a wonderful feature that every object, no matter what color it is, no matter what shape it is, no matter what material it's made of, if it's at a constant temperature, like you put it in an oven and heat it up, it glows in exactly the same way, every single object. And there's a very, very clear spectrum that it has, a certain amount of red light, a certain amount of blue light, etc. So you can try to predict that, theoretically, using the tools that you had in the year 1900, and you get it wildly wrong. So Max Planck comes along and he says, well, maybe when the light is emitted, even though it's light, even though our friends here in England, like Maxwell and Faraday, told us that light is a wave in the electromagnetic field, maybe when it's emitted, even though it's a wave, it's emitted in little chunks, right? Like a little bit here, a little bit there, rather than smoothly and continuously. And with that out of the blue idea, he fit the data perfectly. But everyone's like, well, what does that mean? And it was Einstein who actually said, the difference is the following. Planck said the equivalent of, I have a coffee maker that gives me coffee in 1 cup increments all the time. Okay, I push the button, I get 1 cup of coffee. And that's one little photon, one little particle of energy. And Einstein came along and says, coffee only exists in 1 cup increments. So he said that it's not just that light is emitted by a hot object, 1 particle at a time, but light is particles, is what he said, which is sort of completely incompatible with everything we thought we had figured out in the 1800s. So that's the first sort of particle versus wave-like thing. And then this thing with the atoms, the electrons in the atoms, people were like, why don't electrons fall in? And Louis de Broglie, a French physicist, said, well, if Einstein says waves can be like particles, maybe the particles, the electrons, can be like waves.
Right.
And then that also worked, but it was clearly a sign that something was moving toward the same direction, but reconciling everything took more years than that, yeah.
Okay. We keep mentioning Einstein. Tell us about Einstein. I mean, everyone knows the images and everyone knows the myth, but what was he really, and what did he add, and what did he question?
So Einstein was a smart cookie, as it turns out. I think, if anything, this is almost going to sound silly, he's underrated.
Okay.
And he did win the Person of the Century and the whole bit. But we have this image of Einstein, in the early 20th century with relativity. He came up with space-time, and then space-time is curved, and that's gravity, which eventually led other people to things like black holes and the Big Bang, and it's a big deal. And one of the fundamental things about gravity and general relativity is that it's more or less a one-man show. Einstein was the only guy who was really pushing on that, and he figured it out. Whereas with quantum mechanics, it took 20 people, years to really get this right, arguing with each other back and forth all the time. There's many different contributions from many different people, so you can't point to one person and give them the credit for quantum mechanics in the same way that you can give Einstein the credit for general relativity. So just for that reason alone, he deserves a lot of credit, and he gets it. But then there's this story that you will hear that Einstein couldn't quite cope with quantum mechanics, right? So by the time quantum mechanics is put into its final form, it's around 1927. And there's this image of Einstein as an old man who can't quite keep up with the times. Now, he was like 48 years old. So I don't want to be told that he's an old man at the time. But also, that image is wrong because Einstein understood quantum mechanics better than anybody, including the people who are given credit for inventing it. The difference is that he just wasn't willing to accept that it was done, that it was, he wrote a famous paper, can the quantum mechanical description of reality be considered complete? He thought there was more to the story and we should keep looking. And I think he was right about that. I think that the stories that we were telling ourselves in the 1920s are woefully incomplete. So I do think that, he had some ideas near the end of his life that turned out not to work, but we've all had ideas that turned out not to work. I think that his judgment was really, really good on these issues.
Do you ever wonder how a guy in Switzerland on his own, without laboratories, came up with this? Or is it because it was a complete paradigm shift in a way of looking at things? I mean, do you ever think about that?
Well, Einstein had, in 1905, he had what is called his miracle year, where he has, 4 different papers published in the same journal, any one of which should have won the Nobel Prize. And we do think about that, how in the world that happened. And he was not even a professor at the time. He was a patent clerk, right? And maybe you can say, well, being the patent clerk gave him more free time because, it was not a very difficult job. It was enough to pay the rent, basically. But no, somehow he had this way of figuring out exactly which parts of the phenomena were relevant and which parts were irrelevant, which parts you could throw away and which parts you could keep. In fact, his first major contribution to relativity, there's special relativity that is all the business about the speed of light being constant and the clocks and so forth. That's 1905, and then it was 10 years later, 1915, that he says, well, maybe this space-time is curved and you get gravity. Special relativity was not just Einstein. He was building on things that other people did. In fact, his major contribution was to say, we can simplify everything. There was this idea, there was the ether, this invisible field that filled all of space, right, and light was propagating through the ether. And it took Einstein just to say, if you remove the word ether here everywhere, and you just say light propagates through empty space, you get all of the phenomena correctly described in much simpler terms. All you have to do is give up on the idea that there's an absolute space and an absolute time, which is a lot to give up on. And he was just a genius at giving up on the right things.
Wow, and that probably is the history of great movements in human technology and understanding. People who know what to look at, and then people that can also walk away from previous assumptions.
It's fascinating to me because there's no one right way to be a great physicist. There are different physicists who have very different styles. Just at Caltech, where I am, in the 1960s, we had both Richard Feynman and Murray Gell-Mann, who were the best theoretical physicists in the world at the time, but very, very different styles. And styles come along with different predispositions, different feelings, different intuitions about how nature is going to work. And the dirty little secret of theoretical physics is that it's not an algorithm. There's not a way to go from the data to the correct story. You're going to guess. You're going to say, well, maybe it's this way, maybe it's that way. Different people will make different guesses, and in different historical circumstances, different guesses are going to turn out right. Like Einstein in 1905 made all the right guesses. His intuition was spot on again and again. And then when it came to the 1930s and 40s, when he was trying to unify gravity with electromagnetism, all of his guesses were wrong. And he didn't become dumber. It was just a different time, and different problems were ripe for being solved at that time.
Okay. And yeah, you mentioned Richard Feynman. I mean, he's kind of a legend at MIT and Caltech. My dad actually took that freshman physics class from him, I think in 61 or something.
Yeah, I have Richard Feynman's old desk.
Really?
At Caltech, yes.
Oh my gosh. Gotta make sure that's not stolen from you. That's like
there's a little sign on it at the bottom that says Feynman's desk.
Okay.
So
he's quite a legend over there. But again, a really forceful personality. I mean, personalities matter, because a personality can drive forward an idea, a concept. I mean, look at Stephen Hawking, look at Feynman, look at Einstein.
Yeah.
It's strange that in a field that's about the numbers and about the theory, how a personality can change things.
Absolutely, and no better example than quantum mechanics, really, and Niels Bohr, who was sort of Einstein's counterpart on the other side. Bohr, clearly a genius, did absolutely central work in establishing quantum mechanics. He was the one who figured out, that electrons come in certain orbits and not other orbits, which was a crucial step. But he was a very different personality than Einstein, much more charismatic, gregarious, social. He worked with people. He founded a school and an institute. He had acolytes and followers. Einstein, much more of a loner, just kind of wanted to do his own thing, be left alone. And that was crucially important to winning the marketing battle when it came to the interpretation of quantum mechanics. Bohr said, like, okay, we're basically done, everything is fine. Einstein and Schrödinger and other huge names said, no, we're not done. What are you talking about? And Bohr won, clearly, decisively. Like, he was the one the physics community went along with. And so it does matter. And I think that that's an example where it was a mistake. You know, like sometimes force of personality and charisma and persuasiveness help people accept difficult ideas. Sometimes they kind of hold them back from tackling different ideas.
Right. And I think I saw somewhere you assert that, like, since 1927, we haven't been as curious as we used to be about physics. Can you explain that?
Well, about the foundations of quantum mechanics in particular. So we had this idea, you know, put together by the late 1920s. It was all there was a system in place, and that system had this statement that, you know, electrons or other quantum systems are waves when you're not looking at them, and they look like particles when you are. So the question is that a way station? Is that a partial solution to the correct eventual solution, or is that just it? And the physics community decided that's it. And we're not going to ask questions about what's really going on underneath. We're just not going to worry about that. If you write a paper about the foundations of quantum mechanics, the journals will reject it. Your colleagues will look at you as if, oh, it's too bad you no longer do real serious work anymore. There's example after example of people either, you know, being told not to do this, or people who already had established careers hiding from their colleagues the fact that they were working on the foundations of quantum mechanics. And I think it's finally changing. I think that, you know, both we're kind of stuck in fundamental physics in certain ways right now, but also for, again, technological advances have brought us to the point where we're building quantum computers, and the need to truly understand quantum mechanics is front and center, so people are beginning to take that problem a little bit more seriously.
It only took us 100 years.
Only took 90 years, let's be fair, yeah.
That's strange, but also from what I understand about academia is that it is kind of it's a weird club in that sense, where you can't bring this up and you have to do this and to this appointment. I mean, in a weird way, it's the opposite of the free market.
Well, there is a free market there, but it's a free market of ideas, and you have to persuade people that your idea is worth following. And just like the free market, it's not that you're just, you know, doing an experiment and collecting data. You're trying to affect people's opinions, right? You're trying to, if you're in the free market, you want people to buy your product, and there's something called advertising, and you know, there's supply and demand, but you can try to generate the demand. It's not just there as an objective fact. It's exactly the same thing in academia. You have an idea, your idea may or may not be right, but you certainly have to sell your idea. You certainly have to convince people that your idea is interesting. And ideally, the best ideas win, and I think in the long term, the best ideas win, but moment to moment, a good idea can really struggle.
Right. Talk to me about the Hadron Collider, because I think that's something that everyone watches, they see, and I think most people would say, you know, they're obviously looking into some quantum aspects and some atomic level stuff. What have we learned from the collider, and what have we not learned?
Well, I think this is a great thing to talk about because it shows the difference between what particle physics has become really, really good at and what it's choosing to ignore. So things like what the Large Hadron Collider in Geneva does. This is a giant, 25-mile around ring under the ground where there's these tubes that are emptied out and you shoot protons around them very, very close to the speed of light, 99.999999% speed of light, and they smash into each other. And you ask what comes out, okay? And one of the things that came out was the Higgs boson, discovered in 2012. And both doing those experiments and making the predictions, theoretically, for what's going to be seen by those experiments, that's where physicists are really, really good. I mean, the Large Hadron Collider was literally the most complicated machine ever built by human beings. And the predictions of these particles were made in the 1960s, and then it was seen in 2012. So the predictions are just made by theoretical physicists like Peter Higgs, Francois Englert, Robert Brout, and based on trying to come up with a theory that made sense. You knew some basic features of the world and you knew the math. And just on the basis of that, they were able to see decades into the future and say, if you do the right thing, you'll see a little particle being created. That's just exquisite and beautiful and a real triumph of both human beings trying to understand the world and of the power of physics to get the world right. Just like Einstein in 1915 coming up with general relativity, and then we discover gravitational waves from black holes in 2016. On the other hand, you don't need to understand much about the foundations of quantum mechanics to do the Large Hadron Collider. All you need to know is you smash particles together, there's a certain probability that when you observe what comes out in your detector, you're going to see this particle or some other particle. If you say, yes, but what do you mean observe and measure and all those sort of philosophical sounding questions, nobody knows or cares who works at the Large Hadron Collider. That is not their deal. They want to predict what you will see. They do not want to ask what's really going on at that moment when the measurement is being made.
So in a weird way, it's not that advanced, or not.
Well, it's advanced in one direction, but not the other,
Okay.
right? And so we're choosing to be really, really good at one kind of thing, which is very practical. Like one of the reasons, there's many reasons, but one of the reasons why the focus of physics shifted in this way was the center of physics moved from Europe to the United States, right? Like all of the great founders of quantum mechanics were European, one way or the other. But then the next generation of real geniuses like Feynman, like Gell-Mann and others were mostly American. And the Americans, bless their hearts, but they have a much more practical attitude. They're like, what can I do with this? What can I build with it? What can I make with it? Right. Or at least, even if you're a physicist, what can I observe? What can I see? Right? What experiment can I do? People like Einstein and Bohr were deeply immersed in traditions of philosophy and humanistic inquiry, and people like Richard Feynman were not. They didn't want to hear about that stuff. Right. And so, there's this joke that the motto became "shut up and calculate." And that's not really the motto, but it's a pretty good, summary of what the attitude became.
Okay. All right. And now that's why CERN is in Europe, you think? It's more theoretical.
Well, we had, in the United States, we had Fermilab, which was sort of the competitor to CERN for a very long time. And it's this weird thing where certain kinds of particles were discovered in the United States and certain kinds were discovered in Europe. So Fermilab discovered the top quark and a lot of other very important particles, and they were rivals. But the United States has more or less given up on this chase. We had this proposal to build the superconducting super collider in the 1990s, and it fell victim to the budget battles. And Bill Clinton, who was president, did not really support. He wanted it to be built, but he didn't try, right? And so Congress just canceled it. And it would have been a higher energy machine than the Large Hadron Collider in Europe. And Europe, has gotten their act together a lot better than the United States has. They have, which is amazing because they're multiple countries, right? They have to agree. And so it's both good and bad that there are multiple countries and they have to agree. Like on the one hand, you might worry that there's a lot more failure points. Like any one country can just say, yeah, I don't want to do that anymore. Well, on the other hand, there is a spirit of cooperation and working together. And, okay, well, if France is donating money, then we should also donate money, that kind of thing. Whereas the United States, every 4 years, has a presidential election and they just throw out everything that was done 4 years previously.
Yeah, no, for sure. Now, look, as a common person, how is quantum physics going to be affecting my daily life? And what do I need to know? I mean, these days we're carrying around things that use it all the time, I guess the sun itself, but what are some things that we should know and maybe even prepare us for the future, 10, 20, 30, 40, 50 years from now, when it might make more of a difference in our life?
So there's the answer that I kind of am tempted to give, and then the better answer that I should give. The answer I'm tempted to give is we're trying to do this just because we want to understand the fundamental nature of reality. It's not going to make you a better iPad, a better cure for cancer, a better TV set. The technological implications of quantum mechanics, we can do. We can do those already. The kinds of questions that I want to know about, is there multiple worlds out there? What happened at the Big Bang? These have no direct implications on how we will live our day-to-day lives. I think that's a fair and true answer. But the other thing is, advances in understanding do come along with advances in technology, even if they're unanticipated. The idea that you can build a quantum computer, for example, which Feynman was one of the first people to point out. This might be crucially important to future technology. You're not going to probably have a quantum smartphone or anything like that, but if quantum computers can break codes or simulate complex physical systems that couldn't otherwise be simulated, that might be revolutionary for computing power.
And how does a quantum computer work differently than what we currently have? Just if you had to explain that.
There's a couple things going on. One is if you just have a bit, right? A classical computer pushes around bits, ones and zeros. Right. Quantum mechanics says rather than a bit, you have a qubit, very clever name for a quantum bit, okay? But what it means is instead of a 1 or a 0, you have a combination of 1 and 0. You can be almost all 1, very little 0, or vice versa, or any combination thereof. So you, in principle, every single quantum bit contains an infinite amount of information because it's some number between 0 and 1, right? It's not just either one. The other thing is, much more important actually, the quantum bits can be entangled with each other. And this is something that, guess what? Einstein was the one who figured this out back in the 1930s, that in classical mechanics and Newtonian mechanics, if you're talking about the solar system and you have, the sun and the moon and the earth, they all have their separate things. There's the sun, it has a location of velocity. The moon has a location of velocity. The earth has a location of velocity. In quantum mechanics, you have waves, but you don't have separate waves for the sun, the moon, the earth, this electron, that electron. There's just one big wave function for the whole universe. And that means that the state of these different little pieces of the world can be connected to each other, what we call entanglement. So you have two quantum bits, and they can be related to each other in an interesting way. And that just gives much more room for the computation to happen. There's many more things that can happen. It's not just, I tell you what that bit's doing, and I tell you what that bit's doing. I tell you what the system is doing. And there's all these combinations of what can be going on at once. And so one little quantum computer with 100 qubits can have an enormous amount of information stored in it, way more than a classical computer can. And if we can learn to manipulate that information effectively, it would open up a huge vista for computing power.
And then with a massive amount of computing power like that, a lot of things become possible.
That's right. And also you can use quantum mechanics to, invent new ways of keeping things secret. Quantum cryptography, right. Not just breaking other people's codes, but inventing your own. There's quantum money that can keep your transactions safe. It's much more safe than blockchain or something like that.
Right. Or finding some big prime number to encode
things like that. So we don't know exactly what the quantum technology future is going to look like. But we're getting there. That's definitely a frontier that is moving forward quite rapidly.
So it will be happening in the next 50 years.
Yeah.
Okay.
Yeah.
And this was spoken about by Feynman and even by Einstein in the past.
Feynman, well, Einstein sort of laid some of the conceptual foundation for it, as did Feynman. People like David Deutsch, who's at Oxford, was one of the pioneers there. Okay. But now, like every tech company has a quantum computing offshoot, Google, Microsoft, IBM, right?
Okay.
And you can go online. IBM lets you do your own little quantum computation with they have 5 qubits that you can manipulate or something like that.
Wow.
So
okay. All right. You mentioned parallel universes and the Big Bang. How do you feel about the Big Bang? What should we know about the Big Bang? Some people say it's ridiculous. Some people say it happened. Right. I hear everything these days.
Well, you can hear everything. It's a big internet out there. You can hear all sorts of things. But the problem with the Big Bang is there's no scientific problem, but there is a language problem. We use the phrase Big Bang to mean different things. The thing that we know with complete confidence is that the universe is expanding. Okay, if you look at distant galaxies, they're moving away from us. And if you wind the movie backwards, everything was closer together in the past. And around 14 billion years ago, everything was on top of everything else. Everything was smushed together in an ultra-dense, super hot state. So there's what's called the Big Bang model, which is just that, which is the picture that 14 billion years ago, the universe was in a hot, dense state. It expanded and cooled and developed into the world we see today. Then there's the Big Bang event. There's that moment at t=0, the very, very beginning, and that we know almost nothing about. That's just an extrapolation into the past, using some hopes and dreams about what the laws of physics would be like back then.
Right.
But that might have been the very beginning of everything. It might have been the beginning of space and time. What Georges Lemaitre, who was one of the founders of the field, said, there could have been a day for which there was no yesterday, the first moment of time. Or it might not have been. It might just be a phase the universe went through. There could be space and time before the Big Bang.
Right.
And that's what we don't know the answer to. But we have some good ideas, and we're making a little bit of progress there.
Okay, so people can easily attack it and just say, well, who said this happened here? And then you're like, well, look, this is something that could have happened.
Yeah.
And that's why these people go through, and they go through the real details, like of the every single micro, not even a microsecond, and like this was created then, and this element was created then. I mean, there's all these things that happen right in that first second. Right?
That's right, and we should be very, very careful about distinguishing the parts we're confident in from the parts we're just speculating about. So 1 second after the Big Bang, literally 1 second, we become confident. We actually have data. Because 1 second after the Big Bang, the universe was a nuclear fusion reactor. It was taking hydrogen and neutrons and fusing them together to make helium and other light elements. And we can see that helium and the other light elements, lithium and deuterium. We can measure how much of it there is. We can compare it with the predictions that we get from the Big Bang model, and it's spot on. It's just gorgeous. So that's why Steven Weinberg, a famous physicist, wrote a book called The First 3 Minutes. What he meant was between the first few seconds and the first 3 minutes, we know exactly how the universe was behaving. Before then, before 1 second after the Big Bang, in between 0 and 1 second, we have some ideas that we're kind of fond of, but we don't have any data telling us which of those ideas is correct.
Okay, and before 0 seconds,
Nothing at all.
We just don't know.
We don't even have good ideas. We have fun ideas, but we don't have any ideas where we say, yeah, that's probably right.
Okay, parallel universes, what does that mean, and what are your thoughts on those?
Well, I think it's, to me, the correct way of thinking about quantum mechanics. There's a nomenclature problem because there's something called the cosmological multiverse, which is actually a fairly down-to-earth idea that very, very far away, conditions in our universe are very, very different. So different that we might as well think of it as a different universe. And that may or may not be true, but it's so far away we can't see it and it's hard to know. The quantum many worlds, which are the parallel universes I was referring to, that's actually what I would consider to be much more likely, but also much more profound. It says, what is the resolution of this puzzle that the electron looks like a wave, but then you look at it and it looks like a particle? The answer is, in many worlds, the answer is, well, that wave can be thought of as a little bit of the electron here and here and here and here, and sort of like a superposition of many places the electron could have been. And when you measure it, because of entanglement, this thing that Einstein emphasized, you are part of the wave function of the universe. Also, you're a quantum system. You can be in a superposition. You can become entangled with the electron. And in fact, if you look at the equations, the Schrödinger equation of quantum mechanics, what happens when you look at an electron? It's not that the electron somehow collapses to one particular random location. It's that there's part of the wave function that says the electron was here and I saw it there. Another part says the electron was here and I saw it there. Another part says the electron was here and I saw it there. And the great insight is maybe all of these possibilities actually become real. And you actually get a set of different copies of reality, each one of which has me seeing the electron in a slightly different place. And that sounds crazy and wild, but it is the straightforward prediction of the equations. And so the question is, do we believe those equations? Do we trust them? Or is that conclusion so wacky that we say we got to change these equations, we got to look for better equations somehow? And both options are on the table.
So there's perhaps many parallel worlds right now.
That's right.
And those are all those different observations from those different worlds.
That's right, yes.
Okay. And that's hard for most people to get their heads around.
To say the least, yes.
I think it's hard for most people to get their heads around the fact that what they see isn't what is reality.
Yeah, that's right. So people talk in quantum mechanics about the measurement problem, which is basically what I've described, where we use the word measurement in defining quantum mechanics without defining it, okay? So what do you mean by measurement, et cetera? That's the measurement problem. But equally important is what I call the reality problem. So you talk about the electron being a wave, but then you see it and it looks like a particle. So what is it really? Like, when you talk about these waves, are they a true representation of reality, or are they just a tool that we're using to predict the outcome of an experiment, and the experimental outcome is the real reality, okay? We don't know. We don't agree anyway, let's put it that way. Some of us think we know, but we don't have everyone else agreeing with us right now. So that to me is just a blatant failure on the part of modern physics to not have a clear, crisp picture of what reality actually is.
Yeah, no, very much so. And like for anyone that's had experiences with psychedelic substances, you really even question what you're even seeing in this reality. And we grow up in this physical world, and sure, we can understand a wave and a particle because we grew up there, but what about the 7 other iterations of what things might actually be? And like I said, who says any of this is real? So, I mean, that's why physics is very interesting, because it gets very quickly into philosophy, doesn't it?
Well, this kind of physics bumps right up against philosophy, absolutely. And in fact, many of the best things being written about the foundations of quantum mechanics now are being written by philosophers. And many of those philosophers have PhDs in physics before switching into philosophy. There's a style of asking questions about the physical world that philosophy departments approve of and physics departments do not approve of. To me, it's still a very important part of understanding the world, so I don't really care if you want to call it philosophy or physics. It's trying to understand the world, right?
Right. And it's not very Caltech to come out something.
It's not very Caltech-y. There's a couple of very good people at Caltech doing it, but it's still not. The physics department doesn't want to be involved. Right.
A lot of those places have a history of it being a very practical institution. We measure this. There's no room for anything not physically proven. And yet, to see this problem in a new way or the correct way, you might need to expand the mind. Some of the great men in history did that.
Well, we've talked about how physicists have different predilections, different attitudes, different intuitions. And very common among the set of all physicists is kind of an idea that we want to keep things as simple as possible, right? Like a sort of down to brass tacks kind of approach to doing things. Show me the money, show me what's going to be predicted in your experiment. And that works for a large number of problems, but it doesn't work for every problem. Sometimes you need an attitude that says, let's take a breath, let's think about what all the words mean, let's think about what we're really saying, the nuances of every little detail of the rigorous argument. And that fits very well into a philosophical tradition, not so well into the scientific tradition.
Yeah, I mean, the scientific method of which all my science fair projects were based upon, which is you make a prediction of what's going to happen, then you lay out an experimentation process, and then you compare the results with your prediction, and then you make a new realization of the world.
That's right.
Isn't necessarily work in quantum.
Yeah.
You might need some other elements.
You need to think a little bit more carefully about things sometimes. That's all it is. And, physicists really like, and again, there is a little bit of a cultural shift, and maybe it's changing, but physicists want to be able to make a prediction they can go test in the laboratory right away. And there are parts of physics today where that's just impractical. It's not that it can't be done in principle, but when you talk about the multiverse or the Big Bang, much less quantum mechanics, there are parts of the explanatory apparatus that are out of our experimental reach right now. So the question is, what are you going to do about that? Are you going to ignore those parts? Or are you just going to sort of pretend they're not there? And the way I like to say it is, you don't get to say, I'm not doing philosophy or I don't care about philosophy. All of these people are doing philosophy in one way or another. You can only do it well or do it badly. And I think that a lot of physicists are secretly doing philosophy, they're just not doing it very well.
Do you find ways to exercise your own philosophy brain muscles in order to give you new perspectives on things? Are there people you read or things you do? Because it's all about what you do with the brain.
Absolutely. No, I completely am a big believer in doing things a little bit differently today than you did them last year, right? And so I talk to a lot of philosophers, people in the foundations of physics who are really, really sharp people. And I agree with them about some things and disagree with them about other things. I also talk to people like at the Santa Fe Institute who do complex systems research, which is, again, a little bit different than the traditional physics kind of approach. But it has wonderful promise to wed together ideas from economics and sociology and linguistics and biology and computer science with physics. So I think there's more than enough cool ideas bubbling around out there to keep people inspired for a long time.
Okay. Now I want to ask you about a couple of concepts that have been introduced to the world and to me on the show, but I had a long discussion about the singularity about 6 months ago. I think I had Dr. Ben Gertzel here, who was working on some things out in Asia, and he was telling me this is going to happen. It's only a matter of time until there is this singularity.
Yeah.
We can even define what that is. To where also we have very strong relationships with computers. We become computers. What is your take on all of that? Because also quantum computing could also affect that as well.
Yeah.
But what's your thoughts on that?
Well, I think you have to be, again, clear about exactly what you mean. So literally the word singularity comes from this idea that there's a mathematical curve representing the progress of technology that sort of will become infinitely sharp at some point in the future, just a few years from now, right? That's the singularity.
Right, where someone described it as in like Nobel Prize winning discoveries will be happening in milliseconds because the technology is so advanced to where it's hard to even comprehend.
Yeah.
That's kind of what
So that's complete nonsense. That's not going to happen. Don't worry about that.
Okay.
You can't extrapolate curves going up like this. It's almost always true that if a curve in some progress in some field is moving exponentially, so the rate of growth is not only fast, but growing faster all the time, that won't last forever. It's almost always, essentially always, the beginning of a curve that looks like this, right? You're undergoing a transition from one flat period to another flat period.
Because something is going to break down in those inputs.
Exactly.
Almost it has to, otherwise, well, there's a new reality, right?
Yeah, there's not enough room in reality for everything to be infinite, right? So you can see this in computers right now. Moore's law, which is the rule that in every 18 months, processing speed doubles, has been broken for a while. It's no longer doubling, right? We're not moving that fast anymore.
Okay.
So, but that's okay. But I mean, the broader conceptual issues about the relationships between humans and computers, artificial intelligence, consciousness, minds, uploading, there's a lot of promise, I think, for really cool things to happen. I also, again, in a slightly curmudgeonly way, think it's not quite as close as people think. And I think that it's easy for people to imagine intelligent computers, just without knowing how it would happen, but what it would be like. And so we tend to leap to that. But it's much harder in practice to actually build them. I think that it will happen. There's no obstacle in practice. But we're not as close as we sometimes like to think. We're sort of cheating our way there. Like we're very proud that we can build computers that beat human beings in chess or Go.
Yeah.
In some sense, that's the most obvious skill set for computers to have. Chess and Go are very finitely delineated games. Driving a car or writing a poem is much harder for a computer. Again, they'll get there eventually, but it's a much harder problem. And I think that because it's easy for us to imagine intelligent computers, a lot of people are missing out on the much more interesting and close technological change of the human-computer interface.
Right.
Where we, rather than build computers like us, where we transform ourselves into more like computers, right? Where we implant our brains with the ability to talk to each other. I mean, it's already here. We have phones, right? Which give us a connection to all the knowledge of humankind.
We already are cyborgs.
We're beginning to get there, yeah, absolutely. And it's sneaking up on us.
Right. I mean, it's not in our bodies, but I don't know many people that could survive without their phone not being near them for 5 minutes.
That's right. And that is something where we're just beginning that upward slope. And so that's going to change things by a lot. I am not able to predict how it's going to change things. So on the one hand, I do believe there's going to be huge technological changes. On the other hand, it will not quite be a singularity. We will not be living inside the matrix.
Are you optimistic that we will find a positive and amicable relationship with our technology, or are there dangers?
There's absolutely dangers. There always are. And there's dangers with fire, right? And with cars. We so far have learned to deal with them. I do think that since the 20th century, something has changed because we've reached a level of technology where there are existential risks, where we can commit suicide as a species, right? And so I'm not saying that that's imminent or it's going to happen, but we have the capability to do that, which we didn't before. There's nothing that 19th century people could have done to wipe out all of humanity, right?
And since the 50s with nuclear warheads,
now we can do it. And now we're developing new ways to do it, right?
Right.
And so if you imagine that there's a percentage probability that a new technology will literally wipe out all of humanity, what percentage is acceptable?
Yeah.
I mean,
what is?
Yeah, exactly.
Is it 1%? Probably not.
When you read those stories of the Manhattan Project,
right, of which Feynman was a part of.
Feynman was a part of it. I was at the University of Chicago for a while, where they did the first self-sustained nuclear reaction, Enrico Fermi.
Right, under the basement, right?
In the squash courts under the football stadium. And there was a very real worry that, this was downtown Chicago. They were doing this, right? This wasn't in the middle of the desert. And they didn't know whether, they weren't absolutely sure. One of their fail-safes was a big barrel of cadmium, which you could pour over the reactor to cool it down. And it was held over the reactor by 2 Husky graduate students. The thought being that if a burst of radiation killed them, they would drop the cadmium and it would fall and shut off the reactor, right? Because they were in such a rush to get things done, they didn't step back and wonder about these things. A different version of that worry came up with the Large Hadron Collider when it turned on. And physicists there were very, very careful. They thought very, very hard, and they decided, no, there's no realistic scenario we can think of that would really be harmful. But it's a new kind of worry. I worry about solar flares, okay? Solar flares, we all know solar flares exist. If there's a big one, it can cause temporary disruptions. There's at least a plausible scenario where once every 1,000 years, there's a solar flare big enough to wipe out all electricity on Earth, which would cause millions and millions of people to die, right? And once every 1,000 years—
Does it wipe it out permanently or for a certain period of time?
Well, electricity, yeah, for a few weeks or a few months.
Right, yeah, that's dangerous.
Imagine what that would do, right? Los Angeles, we worry about earthquakes, but the worry about earthquakes is not that the buildings fall over. We build buildings now that will not fall over. The worry is that Los Angeles has these umbilical cords of water and electricity to the rest of the world that will be just cut, right? And Los Angeles without water and electricity is not going to be a pleasant place to live. If a solar flare comes along and destroys the entire Earth's power grid, that's bad. But if it happens once every 1,000 years, no government is going to spend money to prevent it. Like, it's preventable. You could harden the grid, right? But who's going to spend money to do that if it's not going to happen for another 1,000 years?
Right. Okay. So it's about assessing the probability and then making a judgment on that.
Human beings are not evolved to worry about 1,000-year timescales, much less million-year timescales.
Yeah, much less 100-year. You talked about the interface with our technology. I'm sure you've seen Elon Musk and his company Neuralink. Mm-hmm. Are you ready to get those things placed inside your head so we can connect with the phones? And also, maybe you could explain to people what it's all about, because it's about increasing the bandwidth that humans can communicate with computers. Because right now we use thumbs, and it's very low bandwidth, right?
Very low bandwidth. So there's an idea, that you could build implants literally inside the skull that would communicate directly to your brain. Now, the technology's not there yet. It's not going to be next year, okay? People are now building brain-computer interfaces that are like helmets or things that you wear in your forehead, and they're much more crude, but they don't go inside your skull, so that's safer. But if it happened, if it worked, which, again, there's no law of physics that says it couldn't work, so maybe it will, it's sort of a way to augment human cognitive capacities, like we can write plays or write symphonies or create art, but we can't calculate the tip on a bill. Whereas any little cheap, old-fashioned 1970s calculator wristwatch can calculate the tip no problem.
I had one.
We're way smarter than that wristwatch, but here's a task that the wristwatch is way better than us at, right?
Right.
So by putting a little chip in your brain that could just hook itself up to a computer, not only do we have access to Wikipedia and Twitter very, very quickly, but we have the ability to calculate things very, very quickly. Like the computer could look at our visual field and say, you got to slow down. You're in trouble when you're driving down the road or whatever. See things that we don't see and things like that. Now, of course, there's enormous problems associated with this. Just watch Black Mirror. It will warn you about all these problems.
Right.
Once you have a computer in your brain, your eyeballs are video cameras. You can record things, which is good. You're having a birthday party, you want to get the memories, you want to record it without holding up a phone. It's also bad for all sorts of pretty obvious reasons.
Privacy reasons.
Yes.
What else?
Yeah.
Okay.
And so I'm very worried about privacy, about, I just worry that people care about privacy, but there's so much sort of economic, capitalistic impetus and initiative to first do things and then fix them, that it might be very hard to restore privacy once it's gone.
Okay, so that's a concern when it comes to that. I mean, what about the fact that I might be a great artist, but I can't paint? So maybe I have a great concept in my brain, but I can't paint, or I can't write music. But I might have a symphony in my head. With Neuralink or some other process, it might be able to pull it out.
100%. Yeah, no.
That's
so
fascinating.
There is, and I don't want to be too much of a downer. There's so much good stuff going on here. And again, just like the smartphone, there's already the beginnings of exactly this. I had Grimes on my podcast.
Oh, yeah, she's great.
And she's an electronic artist, and she was a undergraduate neuroscience student, and she was, we talked about this. She was never musical as a kid, but in her neuroscience class, she was given a homework assignment, go use GarageBand on your Mac to write a song. And she got so into it, she wrote a whole album, and people liked it. And that's how she writes her songs, on a computer. I was at South by Southwest, which is the music festival, technology festival in Texas, and Sony had this artificial intelligence augmented composing system, where basically the computer would randomly generate some melodies and suggest ways to put them together. And then a human would sort of say, yes, that works, that doesn't work. Here's what I want the beat to be. Here's what key I want it to be in. And it's a collaboration between a computer and a human writing a new song there in real time. And so absolutely, I think that art is going to be transformed in many, many ways by these technologies, ways that, again, we can't even really quite perceive.
Right, it already is, like you said.
It already is starting, and again, we're at this stage of, there's a whole long way to go, more progress there.
Even what we do with our new media is how technology is changing art, and that art is changing society in a massive way.
I mean, I have a podcast, which they didn't exist a few years ago.
Exactly, and I had Dr. Jordan Peterson in here, and the day before, he was at the O2 Arena here in front of 8,000 people, the same place I saw Beyonce perform.
Yep.
And he said, Brian, that would have never happened without the podcast technology, because we would have not known, or people wouldn't know, that they had a demand for long-form conversations.
Yep.
And so,
And again, pluses and minuses. There's disinformation out there. There's polarization, because people fall into their little bubbles and they hear what they want to hear in ways that were not possible before, because there was one TV news show that everyone watched, right? And so the rate of change is much faster than the rate of figuring out how to do it well.
Right.
So we sort of rush into things and then fix them and try to make sure everything's okay. That, in a world where we do have this technological capacity to wreak great harm upon ourselves, is dangerous, is worrisome.
Right, and we might be doing that with our media as well.
Yeah.
How do you feel when you see the latest Flat Earther video or something out there? And I mean, I don't know how you feel about Flat Earth, but
it's probably not right.
Okay, it's probably not right. So when you see that, but you also see that there are conventions and movies and actual pockets of people in this world that believe something based on, let's be honest, a piece of media that was created with the new technology of YouTube, that probably would have never existed, like you said, with the old ways. How does that make you feel?
Well, there were always people who believe crazy things,
True.
Right?
True.
But the flat Earth thing in particular is not the thing that bugs me more than anything. It's kind of harmless. I don't know. I mean, they still fly in airplanes. They manage to get around, right? There's much greater harms out there, I think, and I think that it's very interesting that as good as physics is and technology is, psychology and sociology are bad in the sense that they're much harder to understand the human mind and how people talk to each other than it is to understand electrons and atoms, okay? Yeah. So we're beginning to learn about motivated reasoning, cognitive biases, filter bubbles, and things like that. And we're realizing how easy it is for people to be misled by information. There's this study that is kind of hilarious where politics makes you bad at math. Like you can give people a word problem in math, and people who are good at math get it right, and people who are bad at math get it wrong. But if you phrase the word problem in a politically charged language, make it about gun control or abortion, people who are really good at math become bad at it. They're not able to answer exactly the same problem because it conflicts with their political ideologies, right? And what do you do about that? I'm not exactly sure, but at least now we know there's the problem.
I guess we're learning more about it. All of that IP used to be reserved for religious institutions and cults and things like that. They would use it really well.
Mad Men, like there was always the advertising agencies. It's becoming a lot more scientific now,
Yeah, and we're seeing it happen. So what do you think about the talk that we're living in a simulation? I just want to get your thoughts on it. And from what has been explained to me is that if you agree that we are advancing in technology, and whether Moore's rule is right or wrong, or if it continues, is that someday we will be able to create and build a reality like you and I are experiencing now in say, a virtual reality simulation.
Right.
Then I think the theory is that if that's possible in the future, then maybe that's possible now.
Yeah.
And so what are your thoughts on that?
Well, I think that it is absolutely conceivable that we live in a simulation, and I think it's not true.
Okay.
You're allowed to think about it.
Right.
Maybe it's right. I think it just makes our understanding of the world harder and without solving any problems.
Right.
So in fact, I think you can do a little bit better than that. There's this sort of a strong version of the simulation idea is that we can imagine building computers and simulating little life forms and little civilizations, on our computers. And therefore, we can imagine that there's sort of many more simulated beings in the world than real beings, if we're the real ones. And therefore, most beings in the universe are probably being simulated by somebody. And therefore, we're probably being simulated by somebody. But I think that doesn't quite work, that argument, because there's a lot more that we can build than there are of us, so that would sort of predict that we'd be in the dumbest possible simulation, right? In the simplest, most crude, most low resolution possible simulation to be in, which I think we're clearly not. So I think that people underestimate how difficult it is to really simulate a full world like we see. Like people say, the moon, there's the moon, okay, they're thinking like a video game designer. They're like, don't render the moon when we're not looking at it. But the point is the moon moves around and you have to keep track of it. And basically, roughly speaking, to simulate our universe, you would need a computer as big as the universe, or at least with as much information processing capacity as the universe. So I just don't think that imagining that we live in a simulation really fits with what we know about the world we live.
Okay. Yeah, it's something I've had conversations with. I mean, at some point...
But it's possible. Could be, yeah.
It's possible. At some point, it kind of becomes moot. Sometimes my life definitely feels like a simulation. Nothing else would explain it. When I had Ben Goertzel here, he talked a little bit more about singularity as well, but he said in the future, I want to have 20 of myself that are replicated in various virtual platforms, and I don't want to have to, need my physical body, and maybe I don't need it. And from a guy, I get to talk to a lot of different people in the world, and a lot of them are people that believe our bodies and our minds are kind of all one piece, and that all of these experiences we have are integral in the human experience. I get to someone like Ben Goertzel, and he's like, "What are you talking about? Yeah. That's an ancient way of thinking. That's like a caveman way of thinking. In the future, I'm going to have 20 different Bens. One's going to go here, one's going to go here, and I'm actually going to have a much better life." You're thinking in an anachronistic way. What do you think about those concepts?
I think that there's a couple of reasons. I don't buy it. I don't really go along in that way of thinking for a couple of reasons. One is, if you truly had a version of yourself in a computer, it wouldn't be you. It's not like a little part of you. It's a separate person. They have their own hopes and dreams, right? Like they experience things, they instantly become different than you are. So it's not that you have a version of yourself. It's more like you have an identical twin. No one thinks that identical twins are two copies of the same people, right? They're separate people even though they started in the same place.
Right, and then also they're immortal in the computer, so by definition they are different right away.
Right. Something like that is true. However, the other reason why I think that I'm a little skeptical is a lot of these thoughts are really vastly underestimating the importance of our bodies to our minds. The mind does not come out of the brain all by itself. Like the brain, is connected to the body in a very, very deep way. Like sometimes you get tired, sometimes you get intoxicated, right? Sometimes you fall in love or you get hungry. There are external forces that keep the brain going in a certain way, right? That's a very different paradigm than a computer. Like you can turn on your computer, your laptop, you don't touch any buttons, it doesn't complain, it doesn't get bored, it doesn't get hungry, it just sits there, right? None of these sort of needs that we have as embodied creatures are necessarily part of living in a computer. You can try to simulate them, okay, you can try, but you don't have to. I mean, why would you make a computer that gets hungry all the time, right? So I think that they're just vastly underestimating the importance of living embodied in an environment with needs, with interchange with the environment, where we talk, we breathe, we eat, all of these things kind of matter to who we are as human beings.
Yeah. And now, of course, talking about intelligence being located in the gut, and then the heart having other things in the heart, and then there's a lot of other things besides just the brain as the processing unit. I'm kind of along with you, but it is also interesting to hang out with someone like Ben, where he's just like, yeah, you're looking at it the wrong way, man.
It's great to think about these things, because that's how we make progress, right? Like, we imagine things that are impossible, and then we realize what the mistake was, and then we fix it, right? And we make progress that way. So I'm all in favor of it, and I'm probably wrong about my predictions 100 different ways. But it's good to have all the different inputs from different people who understand different aspects of the problem.
Yeah, for sure. I just always try to make sure I'm not using like a horse and buggy lens on something,
Yeah, it's as Niels Bohr himself once said, making predictions is hard, especially about the future. What we're really good at as human beings is taking phenomena that already exist and imagining them being better, right? So, you have an airplane. I can imagine an airplane that goes arbitrarily fast. I have a spaceship. I can imagine going faster than the speed of light. But imagining new kinds of things is way harder. So that's why science fiction in the 1940s was a lot about rocket ships, not a lot about the internet, right?
Right. Because, that wasn't in our field of vision. So,
And so I think that the relationship between humans and technology and computers is the kind of thing where there will be qualitative changes in what's happening. So it's easy. So we have a computer now, it can do some things, it's easy to imagine making it smarter. But it's harder to imagine the ways in which we will relate to these computers when things really change.
Yeah, and that'll be certain thought makers that put it out there and then kind of make those things happen. And that's when we see those kind of quantum leaps, not to steal one of your terms. But and that's when we see those kind of big advances. And
they're
sometimes
hard to
big
predict,
dreams.
and that's okay.
Right.
Let's not just be too sure. Like, make predictions by all means, but be humble.
Right. I know you've explained this concept before, but I was wondering if you might be able to get your take on it, because I'm trying to get my head around it, and that is this concept called Laplace's demon. I remember doing Laplace transformations at MIT, and I kind of remember understanding them. I don't know if that helps at all here, but I was wondering if you could break that down for us.
Happily, you don't need to know anything about Laplace transformations to know Laplace's demon. Laplace was a brilliant guy. I think, he's also, I joke about Einstein being underrated, but Laplace circa 1800 and Boltzmann circa 1870s are like two 19th century people who I want to be much more known in the popular imagination as visionary thinkers. And Laplace, to my mind, was really the guy who first appreciated Newtonian classical mechanics. Like, Newton invented it in the 1600s, but Laplace sort of got it in his bones in a way that no one else had. And so he points out that in this paradigm handed down by Newton, there's this feature that we now call conservation of information. So if you tell me, if you say I have a pendulum swinging back and forth, and Newton says, if you tell me where the pendulum is and how fast it's moving, I can predict where it's going to go. And Laplace says, well, it's also true that if you tell me where it is and how fast it's moving at any other moment of time, I can predict where it came from and where it's going to go.
Right.
The information you need to predict the future and past is there at every moment. And you can extend that to all of the universe. You can say, in principle, if I knew the position and the velocity of every particle in the universe, and I had infinite calculational capacity, and I knew the laws of physics, to me, the future and past are as clear as the present moment. And that's Laplace's demon. He never called it Laplace's demon. He was an atheist.
Okay. One
of the great stories about Laplace is he wrote this big, thick book on celestial mechanics, and it was given as a gift to the Emperor Napoleon. And I'm sure Napoleon did not read it, but his ministers read it and then gave him a little hint. And Napoleon met Laplace and said, Professor, I see there's no mention of God anywhere in your book. And Laplace instantly comes back with not a very diplomatic response. He says, I had no need of that hypothesis. But he called his demon a vast intelligence. Of course, today we would call it a computer, right? Like a super intelligent computer. But later commentators said a demon that had all of this knowledge. Okay. And quantum mechanics kind of undermines the idea of Laplace's demon because you can't predict the future with perfect fidelity. Right. We don't live in the clockwork universe anymore.
Right. And we also have weird human components. Would that mess up Laplace's demon?
That doesn't mess it up.
You should be able to see that.
But this is, I say that very quickly and very glibly, but let's be clear. Like, I think that human beings are made of stuff obeying the laws of physics. So I think that if Laplace's demon could predict what the rest of the world did, it could predict what human beings did also.
Right.
Now we have quantum mechanics, which means you can't make predictions precisely, but still there are laws. We obey the laws of physics as well as anything else.
And so knowing that maybe Laplace's demon exists, how does that change the way you might look at the future? Everything is potentially deterministic with enough data.
I think that it's not the deterministic nature of the laws of physics that matters, because for all intents and purposes, now that we have quantum mechanics, they're not deterministic.
Right.
What matters is that there are laws, and the laws are impersonal. So if you're Immanuel Kant, then you think that human beings are laws unto themselves. That's what gives you autonomy and agency as a person. It gives you free will, right? Right. And I think that view of human beings is no longer tenable. Human beings are physical systems just like anything else. So does that affect my view of the future? No, because I'm not Laplace's demon. I don't know where all the atoms are. I can't make even very good predictions, much less perfect predictions, right? So I don't know what decisions I'm going to be making for lunch today, much less, the far future of the universe. So the fact that there are laws with this sort of counterfactual feature that if I knew the complete state of the universe and had infinite calculational capacity, I would know what happened in the future. Who cares? I mean, that's great to know, but it doesn't affect how I go through my life.
Right. Interesting to see that they were dreaming of computers kind of in the future, or dreaming of these kind of all-knowing possibilities.
Yeah.
Whereas
that's why Laplace gets a lot of credit. Like he's just really one of these guys. He made fun of Newton actually, because Newton thought that Newton was the best physicist of all time. Like he's better than Einstein or anybody, and he put together our theory of the solar system and gravity and motion and all that. And he was smart enough to know that you have all these planets moving around the sun, but they're also gently influencing each other. So Newton worried about the fact that, if you waited long enough, the planets would get out of alignment and maybe even be kicked out of the solar system. So his solution to that was every so often, and I'm not making this up, every so often God would come along and move the planets back into where they belong. And he was a big believer in God. He was very religious, Newton. He wrote more about biblical interpretation than he ever wrote about physics. And he believed that, he had this wonderful, pristine system, but God had to come in and clean things up every now and then. And Laplace was like, oh, come on. What are you saying? That's silly. And it raises questions about, what happens if you extrapolate into the past as well as the future, questions we're still struggling with today.
Right. It was also the sign of the times. I mean, Newton's in the 1600s.
Sure.
If he had grown up in now, maybe he wouldn't have been as wedded to religion.
He'd be a different person. So I don't know what he would be, but absolutely, France in the 1800s was a period where religion was being criticized right and left for almost the first time in European history. So it's not completely surprising that Laplace fell in with that. Yeah.
How do you incorporate religion into science?
I don't. I think that religion had a good run, and science has sort of moved it out of the way a little bit. Not just science. There are things that religion does, purposes that it serves, that have nothing to do with the scientific goal of describing what happens in the world, right? But what I think is that science has been so successful at describing what happens in the world that a lot of the motivation for explaining things by reference to God or supernatural forces has disappeared. And rather, the challenge that we're faced with now is what do you do about things like purpose and meaning and right and wrong in a world that is just obeying the laws of physics all the time?
So
right?
say religion's been replaced by spirituality, philosophy.
By something, and I don't think that we know. I don't think that, in exactly the same way that we don't understand quantum mechanics. There are people like myself who think that we understand quantum mechanics, but other people don't agree with us. There's not a consensus. And there are people like me who think we have ideas about how to live purposeful, meaningful lives in a world governed by the laws of physics, but there's certainly no consensus. And I would say that as a race, as a species, we human beings have done an even worse job facing up to this problem than we've done facing up to the challenges of quantum mechanics.
And yet, if you polled most of America now, how many would say creationism is why we're here?
A lot of them, but a declining number. The fastest growing religious group in the US are the unaffiliateds, the nuns, the people who say that they have no religious affiliation.
Okay, gotcha.
It's still, being an atheist is still the one thing that will prohibit you from getting elected in any election in the United States. There's a senator from Arizona who is like bisexual, all these crazy things,
or something.
And she's also atheist but won't admit it.
Okay.
Like it's easier to be a bisexual senator than an atheist senator.
And what does that tell you?
Yeah, exactly. I mean, it's changing rapidly as these things do, but that's where we are right now. Yeah.
Yeah, and I think also there's this spiritual component coming in, whereas even if there's no God or creationism, I see this a lot in new media. People want to believe in something else, energy, whatever, something out there. And so it's not like we're out of the woods.
And I think that's just a transitional phase. We're holding on a little bit to a little bit of the remnants of the old way of thinking about things, but it's very much analogous to the quantum mechanics situation. In quantum mechanics, physicists had this problem they were faced with very cleanly and crisply in 1927, and they failed to address it. And something moved to fill the void. That's why there are books on quantum healing and quantum yoga and quantum leadership, and none of these have anything to do with quantum mechanics really, but there was a mystery there that got filled in. I think there's a precisely analogous situation with the meaning of life. Right? Where if you say that it's not because God put us here and the meaning of life is to serve God or understand Him or come to know Him, then what is it? And maybe the answer's not easy, but at least facing up to the question and giving our best effort of giving an answer to it would be useful. And some people do it, but it's not like it's widely spread.
And what is the meaning of life, Sean?
I think it's up to people to create. I think that it's not out there. I think there's no unified, unique answer to that question. I think that different people come to existence with different wants, desires, cares, right? I wrote a whole book about this, The Big Picture, where I say, the mistake is to think that there's something called the meaning to life. There are meanings to life, and we bring them. And you might want to say, well, why do I bring this one rather than the other one? And why am I 6'1"? Like there's a whole bunch of environmental and personal factors that are very contingent and go into making them. It's subjective, but not arbitrary. It's relative to me, but it's not like anything goes. Like there's some things I want out of life and some things I don't. And happily, other people have very similar things that they want, right? Penn Jillette, the magician in Penn and Teller, has this wonderful line where he's a well-known atheist, and I think that he exaggerates the actual story, but he says, someone asks him, if you don't believe in God, what prevents you from just like murdering and raping everyone you want? And he says, oh, I do murder and rape everyone I want. I just don't want to, right? And I think that that's the point. Like, even though there's no divine commandment that we should be nice to each other, most people actually want to be nice to each other in some ways. And there's this project we have to face up to, both personally and interpersonally, to figure out what it means to us to be a good person and to figure out what other people want, and then to learn to live together on the basis of those insights.
Yeah, and I think this is a fascinating time in history where I think a lot of people are coming to terms that these old, ancient religions aren't for them. And yet, I mean, I had Dr. Rupert Sheldrake in here who has a book called Science and Spiritual Practices, and he goes into all of the spiritual practices, those all seem to make us feel really good as humans. They connect us, whether we're fasting or doing pilgrimages or singing together or paying homage or gathering as a group. Like those are all really important to being human and feeling connected and having purpose.
Yeah.
And yet when they get mixed up with a religion that says, do this, don't do this, then people lose interest. So it's a weird time now where people are trying to find a new way of having these practices and feeling connected and feeling that morality you're talking about or whatever,
Right.
without it being, I don't know, potentially poisoned by a religion and everything that it brings with it.
Well, I think there's two separate issues going on that do get mixed up a little bit. One is, you're alluding to the fact that organized religion can have some serious downsides, right? Like in my mind, I know not everyone agrees with me, but in my mind, the fact that the Catholic Church does not allow women to be priests is utterly disqualifying to take them seriously, really, as a view of the world. Like it's just an ancient kind of tradition that is not really changed very much.
Yeah.
Don't tell me that that's like leading the world and being moral. And I get that, and at the same time, I'm very happy to say, the Catholic Church historically has created this amazing tradition of music and art and architecture. And I love going into old cathedrals and looking at the stained glass and listening to the organ music and all that, because they're made by human beings who are really very talented. And hundreds of years ago, that's the tradition they would have moved in.
Right. That was their method of expression as well.
Exactly, right. And then the other, so there's the question of, does putting questions of purpose and meaning into an organized religious context bring some bad baggage with it? But there's another question, which is, how does the universe work? What is reality and how does it function? And there, even if it's not organized religion, I think that there are ways to be wrong about the nature of reality that can lead you astray. And there's certain versions of spirituality that qualify as just not getting reality right. So I think that facing up to reality is very important, and part of that is taking the laws of physics seriously and taking the fact that I obey the laws of physics seriously. Part of it is also recognizing that I would like to have a purposeful, meaningful life. So how do I get that? How do I get that in a way that is compatible with the laws of nature?
It's very much like quantum physics, what I find, is because it's not obvious how you get that, because there's a lot of things going on that aren't visible to the eye.
Yeah.
I used to think when I grew up that if I was personally successful and I made enough money, I would be happy. But I didn't realize that my life was linked with everyone else around me and me contributing and all this other stuff. It took me a long time to figure that out.
There's no shortage of simple, compelling answers that are completely wrong.
That's for sure true. What's the biggest takeaway you want from people to get from this book?
I think I just want to make sure that people know that quantum mechanics is science. It's not magic, it's not mystery, it's not ineffable, it's not impossible to understand. Even if we don't understand it now, it's understandable. And of course, quantum mechanics is standing in there for all of reality. I think that as much as we like mysteries and we like puzzles and we don't know everything, there's no reason to think we can't figure things out. And putting the effort in and recognizing, standing up, facing up to the puzzles that reality presents us with is part of what makes us human and part of what really makes life fun, as far as I'm concerned.
And are you tired of the word quantum being hijacked for all sorts of other reasons?
I'm a little tired of that, yes. And so I think that I'm not going to spare my fellow physicists from blame about this. Physicists don't usually do that. Sometimes they do. But because they have not put their best efforts into understanding quantum mechanics, they've allowed space for misunderstandings to grow.
Right. At Caltech, what are you working on there? Like, what are your plans there?
Well, I have, the last third of this book, I described some of the most modern efforts to use quantum mechanics to understand the origin of space-time itself, the nature of space and time. Why is there space? Why is there time?
Yeah.
Right? We don't know the answers to these. So it's different than quantum mechanics, where I think we don't agree on the answers, but there's some very good suggestions. One of them might be right. The origin of space-time, we don't even have good ideas right now. But I think that what has been holding us back is a reluctance to face up to quantum mechanics, really. So I'm trying to think about space-time, where it comes from, what it is, how it fits into the quantum framework, My philosophy is that rather than starting with some classical theory like Einstein's theory of general relativity and trying to promote it to a quantum theory, we should start with quantum mechanics, that's how nature works, and find classical reality within it.
This whole concept of space-time, for someone that doesn't have their head around that, how would you immediately describe it? Because I think about it sometimes and it still kind of boggles my mind, because most of us grow up of thinking time is this one linear thing,
Sure.
stopwatch, Newtonian, space is this other thing here, and they are completely separate variables in the equations.
Yeah.
But we know that they're not. Or
Well,
we believe they're not.
Yeah, I mean, in some sense, there's a part of it that is perfectly obvious, right? When you want to meet someone for dinner, you better tell them two things: where and when. Right. Space-time is literally where we locate ourselves in the universe, and time is sort of on an equal footing to space in that sense. You need to say when it's going to be, just as you say where it's going to be. But Einstein says that there's a much more profound connection between space and time. And the way I like to think about it is this: like if you have two locations in space, 2 points here in London, for example, you can take different routes through the city to get from one location to another. No one is surprised by the fact that which route you take changes the distance that you travel, right? There are longer routes and shorter routes. And if you had a little odometer that you were pushing along with you, they would measure different distances. Einstein says that time is also like that, with your wristwatch playing the role of an odometer. If you can go from one moment of time now to another moment of time in the future, Einstein says that the amount of time that you will experience elapsing depends on how you move through space-time. And so two people can leave here now, meet up again in the future, and have a different amount of time elapsed on their stopwatches. The reason why it's different, it turns out, this is very amusing to me. Well, in space, the straight line between 2 points is the shortest distance you can travel. Every other path will be longer than that. In time, you can travel in a straight line. You can just literally stay in this chair and just age forward in time. And that is let me get this right, that is the longest time that you can possibly experience between those two events.
Because you're stationary.
Because you're not moving. So It's the shortest distance and the longest time. If you zip out near the speed of light and come back, you will always experience less time having passed, more distance. So it's a trade-off.
Such a fascinating concept.
Yeah, that's cool.
I remember my dad explained it to me when I was a kid, and I was like, what? And Einstein came up with all this in his head. So.
But you only notice if you're moving close to the speed of light. That's why people never notice it in their everyday lives.
Right, for sure. Tell me about ethics and with the work that you do. I mean, the classic one was, we know, Oppenheimer worked on the atomic bomb, the Manhattan Project. Yeah. Feynman was there as well. He was really young, but still. And obviously we're talking about some of this AI things and things like that. I mean, is this something that you and your colleagues talk about on a regular basis, especially if you're in a field that's very analytic?
Right.
There's no God here, there's no this. That's for the university, that's for the Harvards and the Princetons.
Right.
We stick to the facts here.
Yeah.
What happens when something like that creeps in? Because I know it troubled Oppenheimer a lot,
right,
but yet they needed him to do it, and they were the best, and they accomplished something incredible. But then you've got these other ethics implications coming in.
Right, so we never talk about that, no. There's people in my subfield of physics, right, where we're talking about whether it's quantum mechanics or particle physics or cosmology, there aren't any ethical implications, honestly, just because we've moved past a point where there are direct technological implications of what we do. You can, the Higgs boson, you can predict it in the 1960s, you can measure it in 2012. There's not going to be any technological basis for new devices based on the Higgs boson. And I can tell you why, because number one, it takes a $9 billion particle accelerator to make one, right, 25 miles underground, 25 miles around and underground. And number two, once you made it, it decays into other particles in a zeptosecond, in 10 to the minus 21 seconds. Okay.
Zeptosecond.
So I think this is actually, it's worth kind of mentioning because it slipped under the radar. The era when new discoveries in fundamental physics would lead to new technology ended circa the 1950s.
With the transistor.
Even the transistor is still electronics. It's still, maybe quantum mechanics from the 1920s, but then, there's nuclear physics in the 1930s. But basically, by then, all of the particles that exist and persist and have implications for our macroscopic world, we had found. Okay. Of course, we found plenty of new particles and we understand the forces better, but the new particles we find are temporary. They go away in a tiny fraction of a second. So you can stretch with things like pions and muons to find a technological implication. But again, those are from the 30s that we found them. And the new physics that we're learning is great, helps us understand the nature of reality, does not help us build new technology. The new technology comes from taking old physics and putting it together in new ways.
Okay, so it's not something you have to directly deal with. And
probably, the world is safe for my ideas.
Yeah, and the atomic bomb race probably was one of the last times where the physicists really had to deal with that.
Yeah, exactly.
On the cutting edge.
It's true.
Yeah. Tell me about you. What's something you have to do in your daily practice to make sure you can be most effective? I mean, you're writing books. You're at Caltech, you travel in the world, you're on TV. What's something that daily that keeps you on point?
Yeah, I read sometimes descriptions of people's daily routine or whatever. And I'm like, this is just not like my life. I'm much less systematic than any of these things. I think that one of the things about my career is that I do different things at different times, different kinds of things. I do, technical physics research, and then I have a podcast, and I'm on the internet and whatever. I write books, and that's what I like. Like, I can't do one thing over and over again. I can't even do one kind of physics over and over again. And some people achieve enormous amounts by just drilling deep into one little thing, and I much more bounce around from area to area, learn this, learn that kind of thing. So there's no daily routine. Every day is a little bit different, right? As long as I have coffee in the morning and I travel a lot, and it's a shame because I have 2 cats at home, and I'd really rather be with my cats most of the time. And with my wife having a nice dinner and a bottle of wine, everything else is negotiable.
Gotcha. All right, now fair enough. That's good. And what if I were to ask 5 of your best friends, and if I said, what is Sean's superpower? How is he able to do all of the things that he does? What would they tell me it is?
I don't know. I think they'd be pretty deflationary about the idea that I had superpowers.
Well, you're obviously doing something right.
I think, I think I'm teachable.
Okay.
I think that's what it is.
Okay.
So right now in my career as a physicist, I'm pretty good compared to physicists at giving talks, for example. I go around giving talks. I talk a lot on TV shows and stuff like that. When I was in high school, I was on the debate and speech team, and I was terrible. Like, famously, my debate coach and everything, he's like, what you're saying is interesting, but how you're saying it is so dreadfully dull and boring, I just can't even imagine listening to you for more than a few minutes, right? And it's not a natural talent, but I just tried my best to get better, and I have enough openness to try new things that I could improve. Like, I had a friend who said a little while ago, because I had given a talk and she'd gone to the talk, and after the talk I said, what do you think? How could I do it better next time? And she said, you're the best speaker I know, and you're the only one I know who always asks me how I could do better next time. And I said, well, maybe those two things are not unrelated, right? I want to get better. Like, I still take online courses. I still read books in very different fields. I talk to people. That's why I started the podcast, because when I wrote my book, The Big Picture, I wrote about things like neuroscience and computer science that I was not an expert on. So I had to go interview people. I knocked on people's doors, and they were very giving, very generous, experts in their fields. And then when the book was done, I didn't have the right to knock on their doors anymore. Now with my podcast, I can talk to anyone. I can talk to Nobel Prize winners and Pulitzer Prize winners, MacArthur Prize winners, and they'll talk to me. And it's just enormous fun for me. So my superpower, if I'm immodest enough to say it, is not in having any talent other than being able to learn new things and really put them to work.
Right, because you're in a field that classically attracts, I'd say, probably highly introverted people. That's probably fair.
There's plenty, many,
physicists,
many.
It probably is. So the fact that you can communicate puts you way above the fray, and that's...
But I am introverted.
Right.
Like, the introversion is an interesting thing. It doesn't mean you don't want to talk to people. It means it's exhausting to talk to people, right?
Agreed.
And I am totally that. Like I have my very good friend Brian Schmidt, who was my office mate in graduate school, who won the Nobel Prize in 2006 maybe. He discovered the fact that the universe is accelerating, right? He's an astronomer, he lives in Australia now, and he's very extroverted. And like when he comes to visit me, he's like, what are we doing now? Like, what are we gonna, and when I come to visit him, he's like, you wanna go out and do something? I'm like, we did something. Let me just sit in my room and be quiet for a couple hours, right? That's what I really want. Like I like talking to people, I like giving talks, I like going to talks, but I need the quiet time in between to recharge. That's very important. I want to be with my cats and my wine.
Yeah, I'm with you. I'm the same. It doesn't, an introvert can train themselves to be a great communicator, for sure. It just means that after they're done with that, they need to go back and recharge.
Very much.
Whereas an extrovert gets the charge from being around people too.
Exactly. Yeah, people are exhausting, man.
Yeah.
I love them,
sure.
but they tire me out.
And what do you have on your bucket list? Do you want to bag that Nobel Prize before you pass on into the parallel universe?
When I was a kid, when I got into science very early, like 10 years old, I discovered I wanted to be a physicist. And sure, winning the Nobel Prize was the kind of thing you wanted to do. By the time I was in grad school, I understood that number one, winning the Nobel Prize involves a lot of luck. It's not a prize for highest IQ or most creative. You have to be in the right place at the right time. And number two, the kinds of physics I was interested in are not those that lead you naturally to Nobel Prizes. Like, let's say I succeed in understanding the many worlds interpretation of quantum mechanics and convincing everyone else that I'm right. There's no Nobel Prize coming along with that. You have to discover something that is then experimentally verified. I'm much closer to philosophy than would ever be appropriate for a Nobel Prize. So, and actually, prizes are nice, but it's not the thing. The thing about a prize is it means you must have done something good, right? Like it's the doing something good that matters to me much more. So sure, I would love to, really understand certain things about the world that have never been understood before. That's very good. I've understood things about the world that have never been understood before, but they're really tiny, right? Like I've pushed science forward by a tiny amount. So I am trying to be more ambitious now, trying to really dig into the deepest questions that we have. And those are the hardest questions. So there might not be progress to be made, and I won't make any progress. But if I do, it'll be very, very useful.
Okay. And other things on bucket lists? I mean, do you want to have your own television show?
No. Oh, my God, no.
Okay.
The podcast is enough. Like, it's once a week. And I don't have a team, there's no one editing things except for me. So it's very lean and mean.
Good.
And I keep it, literally every episode, both recording, editing, putting on the internet, total of maybe 4 or 5 hours. So once a week I can do that much. But really getting into the media as you do, like doing TV where there's video and lighting matters and things like that, or even a more elaborate podcast with multiple guests and sound effects and things like that. That's more than I want to do in that regime. Because I don't want to stop doing science research or writing books or things like that. I would like to write different kinds of books.
Okay.
I'd love to write a novel, screenplay, something like that. Nice. Writing just brings me great, great pleasure. So I'm trying to work things in my career where I can do physics, I can do other kinds of research. I can do research in the origin of life or computer science or something like that, and do writing and do a little bit of, podcasting or media or something like that, and keep it all going at once.
Right.
So that's the challenge.
Because that fulfills you to be doing different things.
Absolutely.
Okay, that makes sense. And how do you write?
I'm lucky enough, I don't know if it's lucky or not, but I have a lot of friends who are professional journalists, and it's interesting that many of them don't like writing books. They love the 2,000-word article. They can be on the hamster wheel and churn it out every day. Yeah. My wife is one of these people. She loves it. Every day she's posting on Ars Technica, which is the website she works for. Hundreds of thousands of people read her stuff every day. That would drive me completely nuts. I'm in my happy place when you say, write a book, you have 100,000 words, we're going to put you in a room for 6 months and leave you alone, right? Okay. And when I know that I have all those words in front of me to explain things in exactly the way I want to explain them, that's when I'm happiest.
Okay.
And my style is very much, sort of hierarchical, like the title comes first, and then the outline, and then the more detailed outline. And I think about every page I write a lot before I write it. So there's not a lot of rewriting and editing, but there's a lot of thought that goes in before I write it. So I will sit there in front of the computer, not touching the keyboard for an embarrassingly long period of time before I finally write something.
Wow. And how did you learn this process?
Oh, I don't know, but writing a lot. Honestly, give a lot of credit to blogs and the internet. It's a great way to just get the words flowing through your fingertips, because there's a huge barrier to writing that first sentence. And one of the tricks in book writing, for example, is never end the day at the end of a chapter. Because then the next day you have to I have to start a new chapter, right? What am I going to do there? But if you write at least the first paragraph or two for the next chapter, then there's a little bit of momentum that carries you through the next day.
Okay. And did you ever have any classic writing training?
Not really, except a lot of writing. So, I was an undergraduate at Villanova, so not a great physics department there at Villanova. It's good, I don't want to disparage it, but there was no graduate school is what I really should say. So I couldn't take a lot of advanced classes in physics. So what I did instead was take lots of classes in lots of things, whether it was philosophy or psychology or religious studies or history. And all these classes were very heavily writing intensive. So I did a lot of writing, essays and things like that. And I was, like I said, I was on the debate team and writing, giving speeches and things like that. So crafting words into sentences is something that I do think you learn by doing, not by being told what to do.
Yeah, and look, if anyone's watching us that's in, the physics side of the world or the technical side of the world, I can't emphasize enough how important that is, because if you can't communicate your ideas, you might as well sometimes not even have the ideas.
Yeah.
And, speaking still matters, writing still matters.
You have to tell people your ideas, and there's a lot of ideas out there, so not only do you have to say them correctly, but you do kind of have to package them in a way that people understand why they're important, right? That's not bad. That's not, it shouldn't make you feel dirty to make your ideas clear and why they're important. And at the same time, there are people who will never be good at that. And for better or for worse, therefore, we will always need journalists. We will always need professional science writers, because there can be people who are doing wonderfully important science and just don't have it in them, either in terms of interest or ability, to explain to the rest of the world what they're doing. And the skill of not being a scientist yourself, but understanding what someone else has done and converting it into language that other people can appreciate is really, really important, today more than ever.
Yeah, very much so. What was the best day of your life and the worst day of your life, Sean?
The best day of my life? There's just the obvious ones, right? Getting married was a good thing. My wife and I found each other late in life.
Okay.
We were 40-something when we got married.
Is she a physicist
We
as well?
found, no, she's a writer, science writer.
of
She was an English major.
Okay.
And we found each other through reading our blogs. We both had blogs. We read them, and that's how we found each other. We noticed that we were going to be at a conference, and
Okay, that's cool.
it's all downhill from there.
Beauty of technology,
Yeah,
right?
that's right, exactly. And 13 years on, blissfully happy, and really, that's been the best thing about my life.
Fantastic, congratulations.
Yeah.
Do you remember a worst day or a bad day?
There's been some bad days. Yeah, I was an assistant professor at the University of Chicago, and I was denied tenure.
Wow.
And it still makes no sense.
How old were you?
How old was I? Late 30s.
Late 30s.
Yeah.
Okay.
Yeah, because by the time, graduate school, then 6 years of being a postdoc, then 7 years of being a junior professor, yeah.
Wow, okay. So that was a tough moment.
Yes.
But still doesn't make any sense.
Doesn't make any sense, no.
But it also defined your
I
new
landed
adventure.
on my feet. I went
Right.
to Caltech, and I got a great job, and I've been doing good things. And, so at a moment like that, when the people who you thought were your friends and best supporters reject you, you can either decide, in academia, so there's sort of three choices I could have made. One choice would be, this is BS, I'm leaving academia, the field. That's what most people do. Another is, I'm going to keep trying. I'm going to be much better behaved, because I knew that, I do dabble in other things, and I write on the internet, and I wrote a textbook, and none of these things are what academia wants you to do. And so they counted as strikes against me. So I could have said, I'm just going to do everything I can to do the research that will get me tenure at a good university. Or the third option is, I'm going to double down on being who I am. I'm going to do me as well as I can and let the chips fall where they may. And so after reflection, I chose option number 3, and I'm glad I did.
Good for you, man. That's a hard decision to make. at those times, but those decisions define us.
Yeah, you got to choose something, and academia is something where the fact that you do have to make choices is hidden sometimes because the path is so clear if you want to do it in the conventional way, right? Like it's clear what you're supposed to do to get tenure, right. And I did those things, but I did other things that you're not supposed to do. Like I didn't not do the things you're supposed to do, but I did extra things that got me in trouble.
Right. But that also brought you to Caltech too.
No, exactly. Like I have written books, met my wife, live a great life in California, and now I'm expanding intellectually into philosophy and complex systems and other things that maybe I wouldn't have done if I had just stayed a physics professor.
Yeah, and the weather's better. Have you thought about going into commerce, companies, all that stuff?
For 10 seconds, I thought about it. You know, if you're a successful physicist, you do get headhunted by like hedge funds and quantitative analysis firms and things like that. And they mention that there are huge salaries involved. But it's so not my life. I just couldn't do it. I mean, for one thing, it's not like I'm kept going by discovering the secrets of the universe, not by making money, right? Like I like money, I enjoy money, but it's just not enough to keep me going. For another thing, these days when I have a public profile and a Twitter account, I literally talked to one of these headhunters and I said, well, if I were working for this firm, would I be able to still, put things on Twitter? And he said, well, you'd have to run it by their marketing department before you put anything on Twitter. I'm like, all right, I'm out.
Yeah.
Not for me.
Not your style.
Not my style.
Right, okay. So just a microsecond, and that's it.
Yeah, never really tempted.
No, fair enough.
I have very good friends who are, in the startup space, biotech or things like that, and it's very exciting, and I very much admire them, and I could never do it.
Right, I totally get that. What scares you?
I mean, I think that there are real threats to the human race. That sounds a little too broad-based, but we're changing things rapidly, and you can point to specific things like climate change or nuclear weapons or bioweapons or whatever. But just the fact that we do have these amazing capacities and are rushing pell-mell to put them to use without thinking them through, that's bad. And it may or may not have anything to do with it, but we haven't found any aliens talking to us, right? It might be very well because intelligent species, when they become technological, tend to blow themselves up one way or the other, literally or metaphorically. And we might just be one of them. And we might be in the last generation of human beings having fun here on Earth. I think that's, even if it's only a 0.001% chance, that's still very worth worrying about.
Still high.
Yeah.
And what do you think is the biggest threat? I mean, you mentioned biological, nuclear, climate change.
Yeah.
Those are pretty strong. And AI maybe gone wrong. Are those the big ones?
I think, the ones kind of old school here, climate change is the obvious one because it's happening and it's gradual, sort of creeping up on us, and it's going to happen. It is happening, it's going to happen. So there's already a disaster coming that we know about. I think that the proliferation of nuclear weapons is, an old school worry, but one that maybe just because it's been around for a long time, we're not paying nearly enough attention to. I mean, the chance that someone smuggles a bomb into a major city and blows it up sometime in the next 50 years, I don't even want to think about that, especially because LA is one of the easiest cities to smuggle a bomb into. Just sail a boat into Long Beach Harbor, wouldn't be that hard.
Right.
And the only way around that is just to do everything in our power as a population to have the fewest number of nuclear weapons lying around. And we're not doing that a very good job at all.
It's something we don't really talk much about. There's a great documentary called The Fog of War with Robert McNamara.
Yep.
And he went through the Cuban Missile Crisis. Yeah. And I highly recommend anybody watch it. He's passed, and he was the Secretary of War during the Vietnam War.
Errol Morris movie, yeah.
Yeah, a really good movie. And at one point, he describes the fact, because he basically went head-to-head against Fidel Castro and threatened, nuclear war. And he spoke to him afterwards, I think 20 years later. And to the effect of something that Fidel said, he said, you knew that you would potentially be destroying millions of people if this happened. And you were still willing to do it. And he said, yes, I was still willing to do it. And Robert said, this is the biggest existential threat in our world. And sooner or later, someone's going to hit that button. And that's his parting words to us, I think.
Who was the Russian general? Vladislav Petrov, I think. Do you know the story?
No, I don't.
Sometime in the 70s, I think it was. There was a a glitch, an error in Russia's nuclear warning system. And the people in charge of the missiles got a command to fire them, the ICBMs aimed at the United States. And literally, one general sort of went against the operating procedure and said, no, don't do that. I don't believe it. I think it's a mistake.
Right.
And they could very easily, for no good reason other than a computer bug, have launched intercontinental ballistic missiles at the US, who obviously would have fired back. That's just absurdly insane, right? Yeah. And now I think that the real worry is not countries getting into nuclear wars, so there's that hasn't gone away, but someone getting a nuclear weapon and just some terrorist organization or just some crazy person or whatever. Like, it's becoming too easy, and that's infinitely scary to me.
Yeah, can you imagine like 50 years from now, like telling your grandkid, oh, that little black thing on the globe, that's the city that doesn't exist anymore and we can't go there for another 100 million years. Yeah. Why? Oh, because this thing happened. I mean, yeah, it's kind of plausible. And I don't know if you recently watched the Chernobyl series that was on. It's really good. It's a full-part series, but it's, I mean, the Russians say it's not true. Everyone say it is true. Who knows? But I mean, it sounds like also it could have been much worse than it was. And it already had a lot of implications. And it was just kind of frightening to see all that happen. And again, I mean, a bunch of physicists designing something that will never break. And then, of course, it breaks.
Right.
So
the general principle is that since the 20th century, humanity has been infants playing with loaded weapons, hoping that nothing goes wrong.
Yeah. So that keeps you.
Yeah. It's kind of
what would we be surprised to learn about Sean? Something maybe you do in your spare time that would be very unphysicist-like or uncaltech-like.
Unphysicist-like. I mean, the answer that I do give to this kind of question is I play poker quite often. But that's kind of physicist-like, actually. Like, it's probabilities and updating, but LA is only a 4-hour drive from Las Vegas, and so I love Las Vegas. Maybe that's the thing that people are surprised about.
Okay.
Just have a big love affair with Las Vegas.
Why?
Love going there. It's everything I like. I can play poker. The hotels are really nice. The food is amazingly good. Everything's nearby, and there's even my favorite casino hotel, the Palazzo, has a rare bookstore with like first edition Albert Einstein and Jane Austen books in it. Like, I love Vegas because you can walk down the corridor of your hotel and here's a person in a bathing suit and there's a person in a tuxedo, right? And it's just you can do whatever you want, and there's a person in a furry suit cosplaying doing something else. Like, all of humanity bubbles up doing their own things. I was at a poker table once with a woman who had literally just gotten married an hour ago, and she was still wearing her bridal gown.
Only in Vegas.
Only Vegas, exactly.
It's a crazy town. I mean, it's a crazy town with a crazy history. And when you play poker, do you play the man or the woman, or do you play the cards and the probability?
It's got to be both.
Yeah.
But, I think that if you are even a little bit good, mostly it's the extent to which you're playing the other person is that you give them some sort of broad categorization as aggressive or passive, tight or loose or whatever. It's not like you're looking for a twitch in their eyeball or something like that. Maybe you do that, but those can lead you either way very, very quickly. Yeah. It's much safer to actually pay attention to what they do, right? Are they betting all the time, or are they just calling all the time? What is their style, and what are they likely to fold if I raise? Things like that.
Okay. Good advice. Yeah, poker can really be an addictive game. It can get the adrenaline pumping.
It's fascinating. It's a game of incomplete information. You're trying to build a model of your opponent. What would they do in this situation? And it's a game where you, like, literally, John von Neumann, the famous physicist and mathematician, essentially invented game theory because he wanted to become a better poker player. And it works, Game theory can be used to prove that the ideal poker player would not do the same thing in every circumstance. Even when exactly the same circumstances arose, you have to mix up your strategy. You have to do something a certain percentage of time, something another percentage of time. That's very hard for human beings to actually do.
Yeah, and hard for a physicist to understand at first look, because there should always be one right answer.
Right, exactly.
But there isn't in this case, because you're dealing with humans.
If you always did the same thing every time, you could be exploited.
Right.
Very, very easily.
Yeah, fascinating stuff.
Yeah.
Sean, I always ask a few questions at the end. I'm going to ask you, if you could pick up the phone and call up the 20-year-old Sean, I guess you're at Villanova right now, and give that young man some advice, based on everything you know now, what would you tell them? The following success secrets are only available inside the London Real Tribe, where you get exclusive access and insights from our high-performance guests on wealth creation, productivity, leadership, morning routines, health, and well-being. To join our tribe community, go to londonreal.tv/tribe. Now, let's continue with the show. It's great advice, Sean. Look, I was super excited to talk to you, and I'm really glad we had this conversation.
Thank you very much. Been a lot of fun.
And the book is called Something Deeply Hidden. I'm guessing they can get it on Amazon, your website.
Everywhere books are available.
Bookstores. Yeah. Fantastic. And the podcast as well on iTunes.
Everywhere podcasts are available. Sean Carroll's Mindscape. Yeah,
Okay.
and so people are clear, I don't just talk to scientists. I talk to a whole bunch of fun people, and it's really a blast.
Gotta check out the Grimes episode. We can have her on as well. She's fascinating. So great stuff. All the best at Royal Society, Edinburgh. Enjoy the UK. Come see us again sometime. Really enjoyed this a lot. And
glad it worked out.
Just wishing you all the best.
Thanks.
Cool. Thanks, Sean.